Alright, so let's look at an application of bootstrapping. Suppose we want to know the average commuting time for people who live and work in the Atlanta metropolitan area. It is not very feasible to contact all Atlanta residents and ask about their commutes, but the U.S. Census Bureau regularly collects data from carefully selected samples of residents in many areas. One such data source is the American Housing Survey, which contains information about housing and living conditions for samples from the country as a whole and certain metropolitan areas. Among the questions asked were the time in minutes and distance in miles that respondents typically traveled on their commute to work each day. The commute times for this sample of 500 Atlantans are shown in this graph here. The sample mean is 29.11 minutes and the standard deviation is about 20.7 minutes. The distribution of commute times is somewhat right skewed. In fact, it looks like there's one commuter, or at least some commuters, that were as much as 3 hours a day. Based on this sample, we have a point estimate of 29.11 for the mean commute time for all workers in metropolitan Atlanta. Now the question is, how accurate is that estimate likely to be? That is, what is our range of plausible values? To get a range of plausible values for the mean commute times of all Atlantans, it would help to see sampling distributions of means for many samples of size 500. However, we don't have data for the population of all Atlanta commuters, and if we did, we could easily find the population mean exactly, so there wouldn't be a need for a confidence interval. We only have the commuting times for one single sample of 500. So how can we use that information in that sample to assess how much the means for the other samples of 500 Atlantans might vary? And if you're called for bootstrapping, essentially for each of those 500, you put their commuting time on a different card. We would then, shuffle the cards and draw 500 with replacement, calculate the new mean, and then keep repeating that over and over and over again. So for the Atlanta commuters, we compute a bootstrap statistic in the sample mean commute time for one sample. And if we make many bootstrap samples, compute the bootstrap statistic for each, that can help build us a dot plot or histogram of the bootstrap statistics and help us understand the distribution, give us an idea about the standard error. So you see down here, the mean compute times for 10 different bootstrap samples. Just imagine, I do a sample of 500, find the mean, create another sample of 500, find the mean, another sample of 500, find the mean, and do that over and over and over again. And here's 10 examples. So that table shows the sample means of 10 different bootstrap samples of 500, taken with replacement from the original commute times in the sample. Based on the 10 bootstrap statistics, we can start getting a feel for how accurately we can estimate the mean. So note that the hypothetical population we simulate when we're sampling with replacement is actually the original sample value. So we know that original sample value, our pretend population mean, is 29.11. This is going to be the center of our distribution. So thus, the bootstrap sample mean gives us a good idea of how close means of samples of size 500 should be to the true mean. So for the 10 samples we looked at, the biggest discrepancy is actually between the 30.57 compared to our original sample, and that's still about 1.46 minutes higher. So it's within 2 minutes of the original sample. Of course, with computer technology, we aren't limited to just 10. We can actually look at, we get a better picture by taking many samples of size 500. So looking at stat key, choose confidence interval for single mean, median, and standard deviation. One of the data sets included with this is the Atlanta commute time. So I'll choose that. And you see over here in the upper right, this is the original sample that we looked at earlier. You see right skewed. The high was right around 180 minutes. And I can do one bootstrap and you see the dot. I can create another bootstrap sample. Yeah, there's a third somewhere. Yeah, there is. I can do 10 at a time. I can even do 100 at a time, or even more, I can do 1,000 at a time. And so let's say this is 2,113 samples right here. And from there, I can choose to tail. And I can see that I'm going from this run number right here, 27.281, 27.3 is the lower bound of the confidence interval. And 31.0 is the upper bound of a 95% confidence interval. In fact, if you want to change it, if you want to do something like 90%, I just click on the middle value and I'll change it to 0.9. And now that's a 90% confidence interval. But for right now, I'm going to stick with 95%. There's also another option, bootstrap dot plot of. You can actually change it between median and standard deviation. I'll get back to that in a moment. All right. So here's the one I did earlier. This figure shows a dot plot of the sample means for 2,000 samples of size 500 taken with replacement. And this gives us a good representation of the bootstrap distribution for all Atlanta commute times. And based on this distribution, it went from 27.3 to 30.9 minutes. Which, compare that to the one we did a moment ago, 27.3 to 31.0, is almost exactly the same. Here's two others, 27.4 to 31.0, 27.3 to 31.0. You can see that I'm repeating this over and over again, doing 2,000 bootstrap samples, but I'm getting pretty much the same answer, other than slight differences. The beauty of bootstrapping is that it can be used to estimate almost any statistic. So if the bootstrap distribution is somewhat symmetric, we just need the bootstrap distribution to be somewhat symmetric. For instance, the graph here shows standard deviations for 2,000 bootstrap samples of size 500. And while there's a slight right skewness to it, it is more or less unimodal symmetric. Going back to the one here, if I wanted to create my own, I'll choose a bootstrap dot plot of. You see, if I choose standard deviation, now each of these dots is a different standard deviation. If I want to do a confidence interval, I'll choose to tail. And you see my standard deviation is going from 17.4 to 24.2. Now, we do need to have at least somewhat unimodal symmetric. And if you notice, if I try medians, you can see this is not something you would want to do a confidence interval for. This is not a good confidence interval. But I can see that the median is pretty much at 25. But standard deviation, okay. Means, even better. Those you could do confidence intervals for, but not the median, not so much. All right. So let's compute and interpret the 95% confidence interval for the standard deviation from this graph here. And to compute the confidence interval, we make sure we have 95% in the middle, and we have that right there, 0.95. And then from there, the lower bound is 17.4, the upper bound is 24.4. So we are 95% confident that the standard deviation for the commuting time in Atlanta is between 17.4 and 24.4 minutes.